Um, so now we're gonna go over a few things. But before I do, I'm kind of trying out a new thing here where I'm not going to be using slides, but I'm going to be using a notepad, or I guess sketchpad in this case, which I like to use a lot. So let's go over the conservation of mechanical energy. Um, and simply, mechanical energy is defined as kinetic energy plus potential energy. It's pretty simple, whatever. But remember that work non-conservative is equal to the change in kinetic energy plus the change in potential energy. Everything makes sense so far. Nothing too crazy. But guess what? You can use some simple derivation here. So KEF minus KEO. So final minus initial will always be the change in, if you know in like science and stuff, like that's always going to be the denotation. So all I'm denoting is the subscripts here. Final minus initial and final minus initial for here. Using simple math, we get KEF. Sorry, my voice is kind of raspy and dry. Oh yeah, K plus PF. So it's the same thing as KEF plus PF, plus, I guess it doesn't really matter what we do, but I'm gonna just be consistent and do negative KEF minus PEO. So this, you can just factor out a negative here, so it's gonna be KEF plus PEF. And the reason why I'm not really explaining the proofs that much in detail, well, I am, but the reason why I'm just saying like, oh, you could just factor it out, is because I'm going to assume that if you care about the proofs, you're going to know a bit of basic algebra. So yeah, and again, what does this look like? This just gets defined as mechanical energy final and mechanical energy initial. So if the work non-conservative equals 0, what actually happens? So if work non-conservative equals 0, that means this must equal 0. This entire thing. So that means EF has to equal EO. And simply because if work is equal to 0, that means these have to be equal to each other. And why? Well, I guess I can use just this equation right here, EF minus EO, which is just the same thing as this, just rearranged. If it equals 0, then you just add EO to the other side, so they must be the same thing. So yeah, that's the thing here. So if an object remains constant as the object does, assuming work NC equals 0, and that's because like let's just take a parabola here, or not a parabola. I guess let's just say it's a roller coaster. As this thing is going down, the amount of work it does, it's gonna, sorry. The amount of force it has going downwards, and I'll use the word force because there's no other force acting on it. So assume this is frictionless. It goes all the way up here again. And what happens is it'll end up at the same point because the work down here, all of it is being converted to kinetic energy. So potential energy is getting converted into kinetic energy because it's moving. And as we know, potential energy is mgy, so this starting point here. And it's getting decreased because KE is pushing it upwards. So it's getting converted to kinetic, and then as it goes up, the kinetic is going back into potential. So if there's no non-conservative forces, then you're going to be at a negative deficit PE when it goes down, but there's a conservation of mechanical energy, which means that if there's no non-conservative forces acting, there's nothing from stopping the force going in the opposite direction, going back to its original position. Like a conservative force, it would be. It's a little bit difficult to understand, but that's what it means. So yeah, but if there is work non-conservative forces, I mean, you just use logic. The friction would stop it from going all the way back up, and it probably slide back down to not its original position. So that's the logic there of behind 6.5. I'm going to be making the slides later, but I'm kind of short on time, so I'm just trying to get this into my head and drill it in before it's too late. But the next one should be quite easy too.